In this video, I will use conservation of momentum to solve a question about an astronaut pushing a satellite. So the kinds of questions that are going to be asked: how fast would the satellite be moving after she pushes it? How fast would she be moving after she pushes it? And in what direction would the satellite be moving? As usual, I start this problem by drawing a picture and writing out my knowns and unknowns. So these are the things we're given, these are the things I need to find. Alright, so the astronaut's going along 250 meters per second, satellite's not moving. When the astronaut hits, she pushes, transferring all of her momentum to the satellite. And we're looking for the final velocity of the satellite. It's listed on the slide as the final speed and the direction. Together those are final velocity. And it asks for the final speed of the astronaut. Now I know that momentum is mass times velocity. And if she transferred all of her momentum to the satellite, that means her final momentum has to be zero. So if her final momentum is zero, that means her final velocity also has to be zero. Alright, so P final of the astronaut is 0, and that's m times v final of the astronaut. So that means v final of the astronaut is 0 meters per second. Probably should have written here kilogram meters per second. We've got this already. That's 0. What about the satellite? Well, now we have to use conservation of momentum. Sum of the final momenta has to be equal to sum of the initial momenta. Plural of momentum is momenta. So you hear me say that word a lot. So the sum of the finals, that's P final of the astronaut plus P final of the satellite has to be P initial of the satellite plus P initial of the astronaut. P final of the astronaut, we've already been given, that's 0. P initial of the satellite, initially it's not moving, so 0. And P initial of the astronaut. Alright, so P final of the satellite, that's n satellite times v final of the satellite, and that has to be equal to initial momentum of the astronaut, that's the mass of the astronaut, times v initial of the astronaut. We're looking for this one. V final of the satellite is mass of the astronaut over mass of the satellite times initial velocity of the astronaut. 90 kg times 250 meters per second over 2500 kg. 9 meters per second. And since this was in the positive x direction, this will also be in the positive x direction. So you can either define in your picture that's the positive x direction, or you could give your answer here of the velocity of the satellite as the satellite would go in the same direction that the astronaut was originally going.